Well, it's 6 p.m. and this is the Randomizer. I'm Charles Schultz, head of Schultz Laboratories and the Universe Science Center. And tonight we're going to look at a very interesting subject. We always pick a random term, and this one came up and it was a single letter. And I thought, this is interesting. Tonight's subject is G. What is G? This isn't Sesame Street. This is actually the gravitational constant. It is one of the most important numbers in physics. And there's an interesting history behind it. We'll get into that momentarily. What I would say is I encourage everybody to join us as a member at schultzlaboratories.com or universesciencecenter.com. Click on the page, go ahead, get a membership, and support our growth addition of new galleries and materials. Get your Oculus on, walk around, and enjoy the space and learn from it. It's going to be a lot of fun. It's expanding a lot, and we're really looking forward to having more members and more support. And thank you for all those who have so far. So tonight's subject matter, G. G is an unassuming symbol, but it stands for the strength of the gravitational constant. Now, gravity is the one outstanding force in our universe, more than any other, that appears to control the exact structure of space-time, the expansion of our universe, the force that keeps everything in orbit. All of those things are determined by gravitation. What's interesting about gravitation is we have four fundamental forces in our universe. The strong nuclear force is the most powerful force. The electromagnetic force is the second most powerful. The weak nuclear runs a far third place. Gravitation is by far the weakest of the forces. And so what's most interesting about this is in quantum mechanics, people have tried to unify the forces using quantum theory. One force remains absolutely stubborn, will not cooperate, and that's gravitation. The other three forces have been unified. We know a temperature at which all three of them act as exactly the same force. Gravitation is a holdout. It does not submit to quantum theory. So let's have a look at this curious force. And quickly, let's say we took the electromagnetic force as being a strength of 1. Then the strong nuclear force would be over 137 times more powerful than the electromagnetic force. Gravity, on the other side, would be roughly 10,000 trillion times weaker. That's 40 zeros, 40 orders of magnitude. So gravity is so incredibly weak, it takes an entire planet to hold you down, and yet you can easily, with your hand, pick up an item, and it takes the mass of the entire Earth to draw that toward you with almost no effect on you. Gravitation is incredibly weak. It's hard to describe just how weak it is properly. Our minds cannot conceive of the difference in strength of the forces. But I come down to one exemplary scientist when I think about gravitation. And it isn't Einstein, and it's nobody of, within the last couple of decades or anything like that. When I think of gravitation, I go back to the scientist Henry Cavendish, an English scientist. And let me tell you, he was absolutely, in my book, one of the top-notch scientists of all time. I think of Michael Faraday, I think of Tesla, I think of, Cavendish. And in my mind, he is one of the people who most represents what a scientist strives to be. He had meticulous work, excellent accuracy and reproducibility, and he dug into subjects that people thought were all over the map, but he always found an answer, and that's what I find so amazing. Cavendish was one of these fellows who got interested in chemistry very early in his career. In 1783, he did experiments with gases, and he found that if he used acids and metals, he produced a gas which later turned out to be hydrogen. And he did measurements on it and determined some things about it, and he sets his samples aside, and he does some experiments with alkalis dissolved in acids and comes up with carbon dioxide, which he didn't have a name for at the time. And he characterizes it and finds it non-flammable. At that time, there was a theory called phlogiston, which was the great flame producer. And what he didn't know was that as chemistry was changing, the names and terms would change. They actually realized it was an element, a chemical element. So his experiments were done before they even had the names in place. He took hydrogen and oxygen, which he extracted from the air, and he burned them and produced water. So Cavendish was the first scientist to describe chemically the structure of water and do so accurately. Again, 1783 he did this work, so that's astounding. We're talking 240 years ago. So after he figured out the composition of the atmosphere, he even built a device that could determine how breathable, how life-sustaining a mixture of gases was. Again, 1780s. He didn't have electronics. He didn't have any of the things we have. He basically made things and did his experiments. And often he was very good at modifying existing tools to get better accuracy and better readings and more reproducibility. And in science, this is a key. If I tell you about an experiment and the results, and you go to your lab and you do it, you must be able to reproduce it, because that's the hallmark of reality. Everybody does it, they get the same answers, you're on the right page. So after making hydrogen and carbon dioxide and determining the structure of water, Cavendish went on to solve the composition of the atmosphere. He discovered nitrogen and oxygen, measured their percentages, and in the end, he came out with a tiny volume, 1/120th of the gas, which you couldn't account for. Well, that was in 1785, and this mystery gas remained unknown until 1890, when two scientists came to the conclusion that Cavendish, 105 years previously, had discovered argon, which makes up 1.3% of the mass of our atmosphere, but because it's a dense gas, it's 1/120th of the total composition. He was right on the numbers. Cavendish went on to do experiments with electrostatics, and I need to say something here. There are many people who seem to feel that gravitation and electromagnetism are the same thing or different faces. That is absolutely untrue. Gravitation is attractive only. It's a unipolar force and incredibly weak, as I mentioned. Electrostatics are bipolar. And the reason you don't see electrostatic forces over huge distances is because having a positive and a negative, they tend to cancel out. And if you study solid state physics, you'll know there's something called Debye shielding distance. And what that is the distance between particles and other particles where the electrostatic field is shielded by other particles. It no longer is felt. Yet it neutralizes itself out over distance. Now, one of the things that brought the electrostatic thing to his mind was measuring the strength of that force. He was very good at this. He took a metal sphere, which he charged, and he measured and determined that the strength of the pull, the attraction or the repulsion of electrostatics, fell with what's known as the inverse square law. So what that means is 1 over some number squared. If you double the distance, it's 1/4 as strong. If you triple the distance, it's 1/9 as strong. If it's 10 times as far, it's 1/100th as strong. So the inverse square law holds for electrostatics. But what he came to was this. By measuring the strength of the field around this charged metal ball, he realized that it meant that the charge must be on the skin of the ball, only on the surface, and not on the interior. And he was absolutely right. This is what allows the Van de Graaff generator, the ball on the stem, you turn it on, you put your hand on, your hair stands up, a high voltage generator. This is the thing that allows it to work, the fact that the charge is on the surface and not the interior of the ball. Cavendish determined that. So his biggest challenge was taken soon after that. He decided to measure the mass of the Earth, something that nobody had even thought of before. But Cavendish, being a very smart man, figured out what he needed to do was determine the strength of the pull of gravity. Then he could work backwards and calculate how much mass it must take for the Earth to have the strength of pull that it does. Perfectly reasonable. So how do you measure gravity? Well, one thing is you don't do it vertically. You build your apparatus so it's flat to the ground so the force is uniform over it and therefore it cancels out the effective pull of gravity. He built what's known as a torsion balance. Basically, it's a long bar and it's suspended in the middle by a device that can measure the amount of torque that is twisting the rod. He put two dense lead balls, one on each end of the rod, and balanced it on this torsion arm. Then he got two much larger lead spheres and fastened them down so they were immobilized, basically nailed to the ground. Now, he knew that this was an extremely weak force. He also realized that the presence of his body in the workshop would literally distort the readings because he was measuring something of such small magnitude that noise could be a huge problem. So think about this. This is 1798. He built this device. He got it balanced. He left his lab and he took his readings. Now, the force of pull that he measured was 1/50 millionth of the weight of the ball he was using to do the pulling. 50 million to 1. That's extremely weak. And he pulled this off before 1800. And he did it with laboratory equipment that he made in his shop. The end result of this is that he was able to calculate from this pull the strength of pull that the Earth must have. Now, his figure came within 1% of the density of the planet when he worked out the math. And that's pretty amazing. Even today, we're probably only within 3 decimal places of confidence of the strength of the gravitational field. So that's pretty amazing when you really bring it all together. So G is the value of that number. Now, why is it so strange that we don't have an answer to the strength of gravity that's any more accurate? Well, for one thing, gravitation is quantitatively very different from the other 3 forces. We know that the other forces are due to very tiny dimensions that are like parallel sheets of paper next to our universe. They're a part of the geometry that extends in a direction you can't reach, but their influence comes through and affects certain families of particles. So some particles feel only the gravitational force, but not the electrostatic force, for instance. Some feel the electric charge, but not the strong nuclear force. So imagine each of the forces being a special dimension at right angles to us that only influences a certain type of hook, called a coupling constant, that's a part of each particle's makeup. Well, gravitation completely blows it out of the water. It doesn't correspond to the same rules. Now, this is interesting. How do we know anything about gravity other than its strength? Well, it turns out that it's actually pretty easy. We look at something called occlusions. And when you have a body such as the sun, which has a great deal of gravitation, and you aim a telescope at the sun, we know how quickly the sun advances around the sky, around the zodiac. And we also know the differential speed of the stars in the background. We can predict exactly when a star should be eclipsed by the edge of the sun as it passes behind it. The strange thing is, the numbers are off a little. And why would that be? It turns out that the light is being curved by the mass of the sun deflecting space-time. Now, we actually have instruments that we use on the Earth to measure the strength of gravity, and they're powerful enough, or I should say sensitive enough, to determine when there are mineral deposits of metals, for instance, underground. When you are upstairs or downstairs, it literally can measure the difference in the strength of gravitation. Similar devices have been placed in orbit and have measured the deflection of space-time when in orbit around the Earth, and can measure the effect of the sun, the moon, and other bodies in orbit. One of the best scientists of recent times in terms of discovery was Robert Forward, and he found interesting things about gravitation. He would use masses orbiting around a space very similar to the torsion balance described by Cavendish, and he would use them to cancel out tidal effects. His machines have been used on the International Space Station, And on the space shuttle, many times, when they had to do sensitive experiments involving the growth of protein crystals or convection in a hot liquid, and was able to eliminate the tiny little amount of tidal force that exists when you're in orbit around the Earth. And what do I mean by that? If you were to fly on the space shuttle, and you were to measure, and you were right in the center of the spacecraft, for instance, you would move exactly at the same rate as the shuttle itself in orbit. But let's say you were at one wingtip or the other wingtip. They extend beyond the orbital path a few meters. Believe it or not, there is a force of 8 millig's or 8 thousandths of one gravity differential from the wingtip of the shuttle to the cargo bay of the shuttle. This tiny force can be significant in disrupting the flow of heat in a molten liquid or in, as I mentioned, a protein crystal growth. So you don't want to spoil the experiment. How do you get rid of that force? You literally use circulating masses that pull back and eliminate that tidal force. And this is one of the things that Forward contributed. One of the other things he mentioned is that all the mass in the universe is positive. Positive mass always pulls other mass together. But he posed a hypothetical thought. What if you had negative mass? What would it do? Well, negative mass would have to be made of negative energy, and nobody's ever shown that, except in mathematics, to exist. But then again, the positron was predicted exactly the same way, and it was discovered to be real. So maybe there's something to it. But one of the things he pointed out is negative mass would have negative momentum. In other words, if a piece of mass is coming toward you, you slap it to push it away. If a piece of negative mass is coming toward you, you push it toward you to slow it down, because it reacts exactly the opposite of what you expect. What does this mean? In every particle interaction that we measure, positive momentum is the rule. When two electrons repel each other, they do so because one ejects a photon and recoils away, just as if you shot a pistol and you jerked backwards. When the particle strikes the other electron ejects away. So this exchange of photons causes the electrons to move apart and they repel each other. That's one of the key rules of the electrostatic force. But what if the particles had negative momentum? What would happen? If this particle ejects a particle of negative momentum, which we'll call a graviton, that particle would actually recoil toward the ejection. And when that particle of negative momentum struck the target, it would pull it toward the other emitter particle. So this negative momentum, if being emitted by these bodies, would actually cause them to draw together. And that is exactly the case in gravitation. So the question is, where does the negative momentum come from? It turns out I found a very simple answer that I believe is correct, and mathematically it works. Mass placed in space-time stretches the space-time, but how does the space-time react? And I said to my wife Elizabeth, it cries out in negative energy, negative momentum. I think this is the easiest way to explain that by stretching space-time, you are literally creating negative energy, which draws other matter in. The simplest, most direct explanation of the graviton that I can imagine. What's interesting is the graviton is known as a spin 2 boson, or a stress energy tensor boson. Nobody's detected a graviton. They know they should be there. They're exceptionally faint in energy. And so, maybe it simply means that we need to reconsider what we consider to be a force in this case. If gravitons are actually conducting the force of gravitation, it could be a geometric structure and not a field or gauge field as the other forces are. This would explain why it doesn't unify with quantum mechanics, with the other three forces. So those are just my mental imaginings about gravitation based on some experimentation and a little knowledge of physics. Now, what is important about G? One of the things we're really hot on these days is understanding gravitational fields. And right now, the most prominent use is trajectories of spacecraft and orbiting satellites. I've mentioned in some previous talks that the Earth is not a perfectly uniform billiard ball. There are mass cons, which is shorthand for mass concentrations inside our planet. We know that in the distant past, over 4 billion years ago, roughly 4.6 billion years ago, right when the Earth was first formed, a roughly Mars mass and sized body, which is sometimes called Theia and sometimes called Orpheus, had formed in the orbit ahead of the Earth. And at one point, when its mass grew to a certain point, its orbit was unstable and it came sailing in and slammed into our molten planet. It hit in the southern portion of our planet, and its molten core sank in and merged with our own. This explains why the Earth's core is so large in comparison to the rest of the planet. But this is also the event that splattered the material off that formed our moon. And the researchers on the moon, the people who took samples and brought them back, the 12 astronauts that traveled to the moon, a handful of them were geologists. And they were able to determine that this was in fact the cause of the formation of the Earth's moon. And there's a number of other things that work with this theory as well. So in the course of events, the core of Theia sinking into our Earth did not reach a perfect circular or spherical solution. It's lopsided. And that lopsidedness shows up as mass concentrations. Satellites in certain orbits around the equator cannot stay where they are without drifting slightly. G is relentless. It stretches to the ends of the universe. And this variation in the force causes satellites to wander from orbit. So what determines the life of one of these geostationary satellites? The answer is fuel. You must stay in the same place. And in order to correct, you use station-keeping fuel. Typically, a satellite will last 5 to 7 years before this station-keeping fuel is exhausted. Then you have to launch another satellite. So you can see the problem that a minor variation in gravitation can cause. Now, let's imagine for a moment, we'll take a little experiment. Let's say we have a body the size of the Earth. And I know a lot of people claim the Earth to be hollow. This is impossible. And here's one of the reasons why. Number one, the density of matter would not correspond to having a hollow planet. There is no element that is in plentiful supply that isn't highly radioactive and fissionable that our planet could be made of that would be dense enough to have the mass of the Earth and still be hollow. Number two, what would hold it up? It wouldn't work. But most importantly, if the Earth were rebuilt as a hollow shell and all the mass taken out of the center and turned into this, call it just a hollow ball, what would the force of gravitation be? The inside would have zero gravity because the mass of the shell would add up to a field that canceled entirely. So imagine a big rubber sheet and we place a ball on it and it sinks down and makes a curvature. That's a normal gravitational field. And it would have a point where the center of the mass is, and it would come up like, well, kind of like a French horn. What happens in the case of a hollow planet? Imagine instead an embroidery frame, a circle, clipped onto that rubber sheet. Now the sheet comes down and has a flat disc at the bottom. That's what your gravitational field would look like. And that's why nothing would have any weight inside a hollow planet. So there's one more hole in the flat Earth theory, the hollow Earth theory. None of that stuff works. Anyway, G is one of the keys in determining that fact. And it's also one of the most important values in physics. So Cavendish, look up Cavendish, Henry Cavendish. You're going to discover a wealth of information about an amazing and brilliant scientist who helped us define the value of gravity and absolutely did the very first measurements of it. And there's so much more to say, but let me tell you, if I get started, I'm going to run for hours, and you don't want that. So I'm going to also insist that somebody who is truly interested in the ventures we're taking here, go to our page, schultzlaboratories.com or universeciencecenter.com. Click on the membership button and join us. For a small subscription, you'll get to see a huge and growing library of videos and educational material. We're adding more galleries, more content and interactive stuff. Get your Oculus, walk around on the property, see what we're doing, go into the exhibits and play with them. And tell us what you want to see. We'll add more galleries with the content and scientific expertise that you'd like to interact with and learn from. So this is our discussion on G. I hope you've enjoyed it. And we're going to be doing another one tomorrow at 6 p.m. The other randomizers will soon be on the page. So if you go to visit the randomizer page, stay on the page. It will automatically forward you to this chat at 6 p.m. And if you go to the page off hours, don't worry. The previous episode will soon be listed there, so you can click it and see it as well. And if you want, you can just go right down the chain and see all the previous videos. Should be worth a couple of hours of a hot tea and a donut and just watch something interesting and fun. So thank you for watching tonight's episode. We appreciate all of our members and all of our supporters. And there's one last thing I wanted to give you. There's actually a biblical reference to gravitation of a sort, I think, and it's in Job 26:7. And it says, "He stretches out to the north over the empty place and hangeth the earth upon nothing." If that isn't a description of gravitation, I don't know what is. The earth is indeed hanging upon nothing, and I think that that's a very important point to make. So go about your normal existence knowing you're standing on a ball of rock and metal, molten material, floating through the void, attached to nothing. And enjoy it. Have a wonderful day. Thank you for watching tonight.